Alright, hello, my name is Vitaly and thank you for coming. This talk is on applying symbolic execution, or in our case Concolic testing, to the Linux kernel in order to improve code coverage and find interesting paths in the kernel that may contain vulnerabilities. We'll start with motivation for this research project, why we've decided to implement this Concolic execution engine in the kernel, and we'll discuss some of the existing kernel fuzzing frameworks, in particular the ones based on code coverage. So before we talk about Concolic or symbolic execution engines for the kernel, we'll do some brief introduction to symbolic execution, set SMT solvers, and we'll talk about Concolic and execution generated testing as a solution to classical symbolic execution. So things like the state or the path explosion problem. And then finally we'll talk about the design and implementation of our Concolic execution engine in the kernel. And I'll show you zero day as the demo. The bug itself is not very interesting, even though it's in every single kernel version, but the way it was found was quite interesting. It was able to reconstruct the entire state of that XFRM object and get to that vulnerable statement. That was very interesting. So first, why the Linux kernel? It's just one of the areas of personal interest, and Linux kernel is open source, so it makes it easy to instrument. There is no need for dynamic instrumentation, and it's just a great target for static code analysis in general, and symbolic execution or Concolic testing. And lastly, I thought it would be interesting to apply one of those existing program analysis techniques to something as complex as the operating system kernel, and see how well it performs in practice compared to, say, fuzzing based on code coverage. I think now we're at the stage where most trivial bugs are fixed. We've had several iterations of fuzzers. We've started with dumb fuzzers, then template-based fuzzers, now code coverage-based fuzzers. And dumb fuzzers are essentially, they just take some random data, take a syscall or an ioctl and just pass that random data to the syscall, and then mutate that data using some static or dynamic strategies, and then try it again. The next iteration was template-based fuzzers, where you would simply identify every single entry point in the kernel. So things like syscalls, ioctl, socket operations, any path that allows you to pass data from user space to the kernel. And then you would produce a template for every single entry point. So for example, let's say there's a write syscall, and it's expecting the 3 arguments to the function, and the first one should be a file descriptor. So things like Trinity would get a proper valid file descriptor and then pass it to the syscall. And that way you get further down the execution path rather than doing a trivial dumb fuzzing. And the final stage is, I think, code coverage guided fuzzers. A few projects worth mentioning are syscaller AFL, the original kernel patch, and kernel AFL. But they're all based on this same idea of dumb mutational fuzzing with code coverage. And in practice it works well, especially when you've got blobs of binary input data and you have no dependencies on the global state. So think of any kernel subsystem. So for example, let's say an image, right? You can, it's just a blob of data, and then you try to mount that image. So you can fuzz file systems. You can take maybe the key management facility in the kernel, where you're providing keys to the kernel, the encryption keys, or X509 certificates. So processing those certificates in the kernel, they're all good examples of good candidates for coverage guided fuzzers. And the basic idea of mutational fuzzing with code coverage is, first you start instrumenting your code, and because you have the source code, you can do it at compile time. You collect some kind of initial corpus of inputs, and this is easy for file parsers. You just collect a few files and go from there. For syscalls, it's a bit more complicated. but you can still do it via annotations and maybe producing those templates. And then you have this infinite loop that just takes the input from the corpus, mutates it, runs it to the completion, and then if that input results in new coverage, then it's added to the corpus, and you just repeat that process again and again. I think syscaller is one of the most practical kernel fuzzers today, and I think the key word here is unsupervised. So there are many solutions, but it's not just a fuzzer for the kernel, it's a complete kernel fuzzing framework. It contains tools for minimizing and reproducing crashes automatically. It's very easy to use, and the idea is the same, right? It's just mutational fuzzing based on code coverage. The instrumentation is performed using GCC, so starting from GCC version 6, there's this F-sanitized coverage profile, and there is obviously some support in the kernel. And then you take this tracing data and you export it to user space via this proc file system, so a proc kcov file, and there's a user space component that takes this data, mutates it, and shows it again. This was the original AFL kernel patch. I think it was just after or maybe even before syscaller, and it was essentially the same principle. Unlike, say, AFL user space implementation that does some custom instrumentation at the basic block level, AFL patch uses GCC instrumentation similar to syscaller, and then it exports those AFL style traces via dev AFL or dev kcov, depending on the implementation. And in user space, there's this modified version of user space AFL that takes this input data from dev AFL instead of some shared memory region and performs all those mutation algorithms on it. And there are several deterministic and non-deterministic strategies implemented by AFL. So deterministic ones are sequential bit flip, sequential addition, subtraction, insertion of integers, etc. Non-deterministic ones are stacked flip bits, insertions, deletions, maybe splicing of different test cases. Another project that's worth mentioning, just because of its implementation, is Kernel AFL. And what it does is, unlike other projects, it tries to be operating system agnostic. So ideally you can fuzz any operating system, Windows, macOS, Linux kernel, whatever you like, and it does it by having this hypervisor. So it essentially instruments the hypervisor itself. It takes QEMU and instruments QEMU. And it's got two components. The first one is the QEMU that runs in ring 0, and there is a KVM component that accelerates it running in ring 0. And QEMU implements several hypercalls, and guest communicates with the host via those hypercalls, so it's extremely fast, the communication process. But the reason it actually works in general is because of Intel process trace. And if you haven't heard about it, Richard Johnson did a few really good talks in the last couple of years, and several tools based on Intel process tracing. It's a hardware feature available in Intel CPUs, I think starting from Skylake or possibly some iterations of Broadwell microarchitecture. And it collects the traces in hardware. So instead of doing software level instrumentation, the traces are produced in hardware, and then you can export those traces and maybe do some analysis offline if you like. But that's what KFL uses, and that's what makes it work. If KFL used QEMU in pure software emulation, it would be ridiculously slow and just unusable in practice. And this is what Triforce does, essentially, if you heard about the project. Same idea as KFL, but it doesn't support Intel process trace. So it's pure software-based emulation, and it's very slow. Now, symbolic execution is just a general procedure for automatically exploring program paths, or as many paths as you can. And as a side effect, you can generate concrete test cases once you explore the path. And it's a middle ground between static analysis and dynamic testing. It is more sound than dynamic testing. We are likely to explore more paths than just randomized testing. And it's also complete compared to static analysis. So if we find a bug, then that's an actual bug. It's not a false positive, unlike static analysis that gives you lots of false positives. So the idea is to take some language and extend support of that language to symbolic variables, the symbolic domain. So let's say there is a language E and we have integers, a set of integers, we had a set of variables, we can perform arithmetic operations, addition, multiplication, etc. There are conditional statements and so on, and then we extend it with alpha, which is alpha in the set of symbolic variables. And then we take this program and execute it in the symbolic domain. So we explore all possible execution paths. As I said, it's more sound than testing because of that. And then for each path, we collect branching constraints. And so if we say get to a branching condition to an if statement, we take both branches and we can explore both paths at the same time. And as the final step, sort of a side effect, you can generate concrete input to your execution paths. So let's take as an example this simple program, and what it does is tries to get to the bug statement. If we can reach that statement, then we can possibly get a memory corruption vulnerability. So if you take concrete inputs as x equals to 2 and y equals to 3, then z becomes 6, and then we get to the conditional statement if x equals to z. So if 2 equals to 6, then we may get to the next line. But because it's not, we would just skip the entire body of that if statement. So symbolic execution, on the other hand, starts with this symbolic domain, symbolic state, where sigma represents the state of the set of symbolic variables, and pi represents the set of path constraints. And as the first, like before we execute the first line, the set of variables is empty, and the path constraints is always, the set of path constraints is always true. So once we get to the first line, we replace the concrete variables, so x and y, with symbolic variables, alpha and beta. And when we get to the next line, z equals to 2 times y, we have the value of z equals to 2 beta. Right, so essentially just replacing the concrete variables with symbolic variables. And now we get to the first conditional statement, if x equals to z. And at this point, we've got two paths. We can go either in the true, take the true branch, or we can take the false branch. If we take the true branch, then we get the set, the path conditions on the left. So alpha equals to 2 times beta. If we go in the opposite direction, then alpha is not equals to 2 beta. And obviously this set of path constraints on the right is not feasible. Right? So alpha is always equals to 2 beta. So you can just basically eliminate this path and don't go that branch. Don't take the path that leads to the false branch in this case. Now we get to the next conditional statement, if x greater than y plus 5. And again, two possible outcomes. We can go in the left direction or the right direction. If we take the left branch, then the next path condition becomes alpha is less than or equals to beta plus 5. And the right branch becomes alpha is greater than beta plus 5. Right? And that's what we're solving. So now we have two sets of constraints. So for the first path and for the second path. So for the first path, we have to solve alpha equals to 2 beta, and alpha is greater than 2 beta plus 5. And for the second one, the second condition is alpha is less than or equals to 2 beta plus 5. Right, so when we solve that concretely, we get two inputs. let's say for the first path, the input is x equals to 20 and y equals to 10. And for the second path, it's, say, x equals to 2 and y equals to 1. So both paths are feasible, and we can take them at the same time if we like. But we now know the answer that we can reach the bug condition, and we have concrete inputs to reach that statement. So the actual symbolic execution algorithm is quite simple. It's just a for loop. It starts by creating this task. So first the set of path conditions and the set of symbolic variables is just empty, and PC represents the instruction counter. So let's say the first instruction that you take. Then we add this task onto the work list, and the work list, let's just say it's implemented as a stack or a queue. And then we keep checking this work list until it's not empty. We take the first task from the list and we execute it, and if it forks, so it forks if there is a conditional statement like the one on the right. So if P, then do something else, do something else. Then we create two new tasks, right? So first one would be we check that pi 0 and the current path is feasible. Then we add that task to the list. If pi 0 and not P is feasible, then we add the other task to the list. But it's also possible then both branches can be feasible, so we add both tasks to the list. And we just keep doing that until we run out of tasks, or until the work list becomes empty. If SMT solvers are essentially what solves those constraints that I showed you. They take the paths and they give you the concrete inputs at a high level. And SMT stands for Satisfiability Modular Theories, or sometimes called SAT++. And that's what basically decides path feasibility. And yeah, generate inputs for paths and bugs. And essentially they're just the front ends to SAT solvers. Right? So it's SAT plus some theories. And there are different theories. There's theory of integers, theory of arrays, vectors, uninterpreted functions, and so on. Right? So what they do is an SMT solver is just a SAT solver plus some formula solver. Theorem solver. And it takes the input, it communicates with the theorem solver, and it gives you the answer, yes, the path is feasible, or the path is not feasible, or unsatisfiable in this case. The problem is that even nice problems are NP complete, but in practice they actually perform quite well. So there are different theories, integers, array, bit vectors, and so on. And in terms of implementations, there are two well-known ones, is Z3 by Microsoft and the STP. We've implemented both of them when we've decided to implement this Concolic engine in the kernel. And from personal experience, Z3 performs slightly better than STP. And I just find bindings for Z3 a little easier to use. Now, the limitations of symbolic execution is the path explosion problem. This is the main one. So let's say you've got three variables, A, B, and C. You make them symbolic variables, alpha, beta, and gamma. And then you've got this branching structure, if A, else, if B, else, if C, else. So essentially it's only three variables, but it's now 8 program paths that you can take. And if you take something as complex as the kernel, one of the, say, syscalls, there is a very complex branching structure, especially for ioctals and things like that. So there is this path explosion problem. The other issue is loops on symbolic variables. So if you've got just, say, a while loop that operates on this symbolic variable, and A is defined as an integer, 32-bit integer, then you've got potentially 2 to the power 31 paths in this case. And this is very problematic. We often have loops on our kernel execution paths. Non-linear constraints we cannot solve. So if we've got something non-linear that just doesn't work and we have to simplify expressions, and I'll talk about concretization a bit later. The problem with symbolic execution is that it can be very expensive, as you've probably guessed. There are lots of possible program paths, and you need to query this solver, either Z3 or STP, every time you decide to take a certain path. And yeah, obviously program state has many bits as well. So depending on the input, on the user input to syscalls or ioctls, the structures can be quite big. Symbolic execution can fork at branching points. So when we have this conditional statement if, we can fork and create two paths. And then both paths can be feasible. And the question now is, how do we systematically explore all the paths? Right, so what we can do is we can check feasibility during execution and then queue feasible solutions, meaning that every time you get to a conditional statement, to an if branch, you query the solver, and if the path is feasible, then you use the path and you put it on the queue. If not, then you just discard the path. That's one solution, but that becomes very expensive because every single time you have to query a solver. The other solution is called Concolic execution, where you basically run the program with concrete values and you generate path constraints sort of on the side. Right, so yeah, the solution is to mix symbolic execution with concrete or dynamic testing. And there are two approaches. One is the Concolic execution by Godfroy and Zen, and the other one is execution generated testing by Kadar. So the idea of Concolic testing is to just take the program, execute it with concrete inputs, and then when you're executing it, you collect path constraints during the execution. And that way you explore all paths sequentially. So let's say, unlike symbolic execution where you fork and you have to explore two paths at the same time, in this case you just keep exploring paths sequentially. You take one path and you keep exploring it until it terminates, for example. And you use concrete values to solve problematic constraints. So this is called concretization, and I think I have a slide later. But if you cannot solve a certain number of constraints, you can simplify the expression and you can replace one of the variables by a concrete value. So this is an example of Concolic execution now. We start again with concrete values. So let's say x is equals to 5 and y is equals to 2. We get to the z statement, z equals to 2y. So z becomes 4. And now we get to the first branching point, x equals to z. So is 5 equals to 4? It's not. So we have this constraint, alpha is not equals to 2 beta. Right, so we just concretely executed the statement, and on the side we keep sort of keeping those constraints as well. We're saving them for later. So what we do next is we take this constraint that we saved and we negate it. So if it was alpha not equals to 2 beta, now it becomes alpha equals to 2 beta. And we run the, say, Z3 solver and we get a solution, concrete values as the input. So the concrete values, let's say x equals to 4 and y equals to 2. Right? So alpha is 4 and beta is 2. So we rerun the program with these values and we just keep repeating this process, generating new inputs. Right, so now we get, because x is equals to 4 and y equals to 2, we get to the next conditional statement, x greater than y plus 5. And on the right you see the actual constraint, the full path constraint, alpha equals to 2 beta, and not alpha is less than or equals to beta plus 5. So again, we negate this constraint. Alpha now is greater than beta plus 5, and we generate concrete inputs. When we do that, x becomes, let's say, 20 and y becomes 10. And in that case, we can reach the vulnerable condition, the bug statement, the assertion failure. Now, in terms of differences between Concolic execution and execution-generated testing, with Concolic execution, we explore paths sequentially, and this is really ideal for something like the kernel. and it's guided by concrete inputs. So at any point, if we can't solve the constraints or if it becomes too difficult, we can just use concrete values. With execution-generated testing, on the other hand, you have to fork execution for each path, and it's guided by symbolic execution, unlike concrete values. And this is not really practical for something like the kernel unless you're doing this hypervisor approach where you're instrumenting the hypervisor. Also, execution-generated testing dynamically checks if all operands are concrete, and if so, the operation can be executed concretely. So, for example, this void test function with a single input, let's say it's a user input x, and then y equals to 2, z equals to 3 times y. So obviously the value of z does not depend on x, on the user input. So that becomes a concrete value and we can solve it concretely. And that's essentially what execution-generated testing does. There are different search algorithms when guiding the search and exploring the paths, and the easiest ones are depth-first search and breadth-first search. So depth-first search is quite easy to implement, but it can get stuck. So imagine you exploring the path and you just keep going deeper down the execution path, and then that path never terminates. So you're just getting stuck in that a single path, where breadth-first search tries to explore as many paths as it can, rather than going deeper down the execution path. There's also randomized search, where you just pick at random a path. You can set a timeout, a random timeout, and just restart the path if you don't find anything interesting. Or you could set a priority to each path and then choose paths at random among paths with the same priority. The only downside is really reproducibility if you do it that way, but that can be easily solved with pseudo-randomness if you keep the seed value. And I guess lastly, the generational search, and it's really a combination of BFS and coverage-guided fuzzing. The way it works is, let's say at generation 0, you pick one path at random and you run that path, and then at generation 1 you take paths that you've discovered at generation 0, you negate one of the branches and you produce a new prefix, and then you solve that prefix path, and then you do this again. So for generation n, you would branch off generation n-1. There are two key implementations, and most symbolic execution systems or concolic execution engines are based on either Dart or exe. And Dart was a concolic executor, while exe uses execution-generated fuzzing. So things like CLE that you're probably all familiar with, it's based on exe, and it symbolically executes this LLVM bitcode or BC files, and it uses fork to manage multiple paths. So it uses execution generation testing, but for path exploration it's got a few strategies. It combines random path exploration with coverage-guided fuzzing, and it is part of LLVM distribution. Now, Sage is not really a kernel fuzzer, but it's a great project. It's well known, and it's just a very good implementation of a concolic tester. And it's been used for Microsoft for a long time, especially for fuzzing various file paths, Microsoft formats, JPEG, PPTs, doc files. And this is really the ideal scenario for concolic fuzzing. You have input-output behavior, you have some kind of input file, and that produces some kind of output file. And this is likely to terminate in this case, so that's really ideal. The only concolic or symbolic execution engine for the kernel that's worth mentioning is probably S2E. If you haven't heard about it, I suggest you read their research paper. It's not specific to fuzzing the kernel itself. It's just a general framework for software exploration. But because it's based on a hypervisor implementation, so they instrument the hypervisor, you can actually fuzz the kernel. So it's a virtual machine augmented with symbolic execution, and they've got several module path analyzers, and they can do very nice things. They can reverse engineer certain malware. They can do symbolic and concolic execution. But they call this technique selective symbolic execution, and essentially it's just a combination of combining symbolic and concolic, and they keep switching between the two. So depending on the path constraints, depending on variables, they may decide to go with concolic and then switch to symbolic. The implementation is quite interesting. They use the dynamic binary translator in QEMU, and if you haven't heard about it, it's just a for loop. And all it does is fetches the instruction, let's say your x86 instruction, and converts it to, if you're emulating ARM, it converts x86 to ARM. And it does it per instruction. So what they do is they take x86 instruction and convert it directly to LLVM bitcode. And then they can operate on the LLVM bitcode. They can use the existing frameworks such as CLI. The only downside of QEMU is, again, there is no hardware acceleration. It's done at this software emulation level, and it's extremely slow. Especially if you use this classical symbolic execution where you fork. It actually forks to instances of QEMU. It does have parallel support for multi-cores, but eventually we just run out of cores, and it becomes very slow. It'd be like one execution per second or so, maybe less. Now, because of this, we've decided to implement our concolic execution engine, and we've decided to implement it in the kernel, unlike this hypervisor approach. And the idea was to improve code coverage and just automatically generate concrete input test cases. So if we find a bug, we can just automatically generate user inputs that can trigger that bug in the kernel. It has a modular design, even though right now there's only one module for path analysis, but you can add more modules, and the idea again was performance really. Because of S2E, it's the performance in terms of executions per second, it was quite slow, and we thought if we implement it in the kernel natively without any hypervisor support, it would be extremely fast. And finally, we wanted to build something specific to the Linux kernel. So we're not interested in any other operating systems, or we're not interested in making it operating system agnostic. The philosophy was just make one tool that works well, rather than trying to implement this Swiss knife for every single operating system. And this would also allow us to get fine-grained control over this fuzzing environment. So, for example, I'm not interested in fuzzing, let's say, syscall entry points. There's nothing there. So let's say I'm interested in a specific subsystem, and I'd like to instrument that subsystem specifically. So that was the idea behind the project. This is the actual overview of the design for a single instance. There's this instrumented kernel, runs in ring 0 natively, or you can run it in a hypervisor, and it generates those path constraints and exports them via the proc file, so it's similar to like proc kcov for syscaller. And then there are two components in user space, the solver agent that runs Z3, and there is a kernel tap agent. So the solver agent solves the constraints, and sometimes you get constraints that depend on global variables, or global state of some variables. In that case, it passes it to the kernel tap agent, and it tries to dynamically instrument the kernel. So make those global variables symbolic, dynamically using k-probes. We're using DFS path search. It was just the first implementation, but it performs quite well in practice. And concrete data is generated randomly, so when we need to either use this concretization technique or choose some concrete value, we just do it randomly for now. So path constraints exported via proc SMT, as just binary blobs, and then those blobs are passed by this user space agent solver Z3. But we also have bindings for STP. And when you reach this global constraint, dependency on the global constraint, we use k-probes for the state variables. So it just dynamically instruments those global variables. In terms of instrumentation, we've considered a few options. First one was LLVM, but we've had some issues with architecture-specific code, especially on x86. It just didn't work quite well. Then we looked into GCC link time optimization. And what it does is allows you to optimize different compilation units as a single module. So it's just a pass of GCC where you can hook and perform your instrumentation at that level. But that didn't work for the kernel. Works great for user space, but there are some issues with the kernel. Maybe latest versions will fix that. So we've decided to go with just a custom GCC instrumentation, and it's per basic block at the moment. It's quite ugly, but it's working. The path constraints are stored in this kernel address sanitizer shadow memory. We just needed some space in the kernel where we can just allocate that. And at the moment, obviously, you cannot use kernel address sanitizer and our fuzzer at the same time. So we use concretization a lot. There are many complex execution paths. There are many architecture-specific optimizations in the kernel, and we just have to make some values concrete. So complex, paths with loops. This is quite often. Infinite loops. We've got non-linear constraints that we cannot solve, and we've got architecture-specific code. Or sometimes we get constraints. We go down the path and collect so many constraints that we just can't solve it. That just becomes too difficult. That's when we use concretization. And down the bottom, you see the example for one of the syscalls, let's say set rlimit, and it takes this user pointer to a structure and copies that data to something that's allocated on the kernel stack. Right? New rlim is allocated on the kernel stack, and then just copies that data from user space because it cannot use it directly. And every single syscall pretty much does that thing. So we can optimize some functions like copy from user, because if you look at the implementation, it's now written in assembly mostly. And we know that this function works as expected. It's a pretty small function, and we can just verify it manually. So in this case, we can say that, well, now make new rlimit the new symbolic variable instead of the user input variable. Right? And we do those optimizations quite often. So I've mentioned this global state. It's done by instrumenting dynamically with k-probes. An example would be down the bottom where you see static in state. So let's say this is a global variable, and then there is some function like kernel entry point that takes two user inputs, x and y. And then if the state has some value, then you use those x and y user inputs, otherwise you just skip them. So, and there is some other execution path in the kernel that operates on this state variable, but it's a completely independent path. And the idea is to instrument the state, so when you see that dependency on the state, you make the variable symbolic, and then you try to reconstruct that state, sort of going backwards from this point. We do implement several optimizations, and this is really taking from the squared E paper, the expression simplification. They have this bit field theory expression simplifier, and the idea is that if you have something like return, say 1000 in hex, and this is a standard page size in the kernel, what that statement tries to do is clear the 12 bits to align the address on the page boundary, and this is quite often. And let's say alpha is the symbolic variable. So we know that the lower 12 bits are zeros. And if we end those values, it doesn't matter what the 12 bits of alpha are, because they're going to be zeros. Right? So we do those little optimizations, but they really help when you're trying to solve huge constraints, number of constraints. So for the For the fuzzing targets, we've had a few file system subsystems in the kernel. I've decided to go with IP XFRM, and this is essentially the IP framework for transforming packets. It's used for IPsec implementations for encoding the payloads of packets, and it's also used for compression in mobile IPv6. And it's got states and policy objects, so there are different states and objects, and there are functions that operate on those state and policy objects. And this was just a perfect candidate to verify the Concolic execution engine. So we go to the demo. There is a user space tool. So IP XFRM state would show you the current state. And the state is essentially the object in the kernel that keeps all the information, such as the encryption key, the source IP address, the destination IP address, the sequence number, and so on. And then various components of the kernel, some separate execution paths operate on that object. And right now you can see the state is just empty. So the idea is that the execution engine would reproduce the state all by itself. It might take probably a minute. But this bug was found probably within 5 minutes on a laptop in a VM, single core VM, when I was on my flight here. Hopefully that works. I think last time it took less than a minute. But this time it may take, okay, we've got a state. And you can see that the fuzzer was able to basically walk backwards and reproduce that state. We've got the des encryption key set. We've got all the variables we need, SPI, the request ID, the transport mode, etc. And it even generated the source and the destination IP addresses. Even though they're not real, they don't belong to my VM, but it's still going to work. Let's see if... Okay, I think it crashed. Yep, there you go. And the bug was in the XFRM user. Somewhere in this function, when it sets the replay is send value, and this attributes object is actually a global object. So what was nice about it is that this object is being set by a completely different path. And the fuzzer was able to reproduce the original path, reconstruct this object, and then trigger this kernel path. There's some future work, obviously. This was just a proof of concept, and it's mostly broken. The next step would be, I guess, to use the source-to-source compiler. Currently, we do instrumentation at this basic block level in GCC itself. It looks quite ugly, so if we use source-to-source compiler, we can do it at a higher level, and it becomes now very complex. We can combine different path search algorithms, obviously more constraint optimization. And right now there is no central manager like syscaller, for example, that schedules VMs and can set timeouts, restart VMs if they crash. It's just a single instance, right? And if it crashes, you have to just restart it manually. But again, this is a proof of concept. What's interesting for me in terms of research is that global state and reproducing that global state with symbolic execution. So when you have these multiple independent execution paths, you have global state variables and just reconstructing the path going backwards. So I guess that's the next step in this research area. All right, thank you. Question? Yeah,
Right.
got a few.
You were talking about execution paths which are independent of some kind of certain global state. Can you use this to kind of solve this branching explosion, this combinatorial explosion of execution paths by identifying paths which are completely independent of each other?
It's possible, but you'd have to do a bit more work. So static analysis in this case. First, build some kind of maybe abstract syntax tree for the entire kernel, identify those paths, and then have like a map and keep referencing that map. But in theory, it's possible. It's just a lot of work.
But it's not really practical?
Depends on how much time you've got, but yeah.
Okay, thanks.
Yeah, hi. It seems like if you're fuzzing in a live kernel and you said you have like internal states, they might not be deterministic. Do you have any ways to make that more deterministic, to maybe reproduce it easier?
Yeah, this is the problem with non-determinism. Not really. So right now there's a lot of concretization and just assuming that this is what you should get. So for example, that even that function I showed you, copy to user, where we say, okay, we know that the return value is this from this function, assuming the inputs are correct, but it may not be, right? It might be a bug in copy to user. So a lot of assumptions, a lot of concretization. But the idea was really to compare code coverage guided fuzzing to the one based on concolic execution.
Any more questions? Thank you for good talk. You have some evaluations about effectiveness of your approach comparing to, general, maybe dumb fuzzing or coverage guided fuzzing. I mean,
yeah,
with and without concolic execution.
I guess we would have some results for the probably next talk, but at the moment this was really a dirty proof of concept, whether this works. But it would definitely be more sound than just testing, just dumb testing, for example. I'm assuming it would be more, in terms of code coverage, it would be definitely more than fuzzers guided by code coverage. I mean, if you take this path, if you take, say, syscaller now, and you try to fuzz this particular path, you would never find this vulnerability.
Okay, I have another question. Could you tell a little bit more about the way you extract
constraints from actual code. I mean, you
Yeah.
need constraints to solve it with constraint solvers.
Yes, so this is done at the basic block level. So this is actually implemented in GCC. When we compile the kernel, we insert those like trampolines, instrumenting code. And every time we take a branch, so for example, you get to a conditional statement and the conditional statement depends on your symbolic variable. If that's the case, then you generate the constraint. And this is done at the basic block level in GCC, so written in assembly. And
Okay, how about symbolic variables propagation or something like that? I mean, what about some variable evaluated based on another symbolic variable, so it must be also symbolic, I think.
yes, that just propagates. There's no problem with that. The only problem is when you have some kind of operations that make it non-linear. So you have a variable that depends on another symbolic variable. And if that becomes non-linear, then you can't really solve it. You have to make one of those concrete.
I mean, you need something that track these computations to propagate symbolic values. I just can't understand how it works.
It's just, so this, let's say when you get to the assembler level, your symbolic variable is in a register, right?
Mm-hmm.
And you just copy the state of that register. So there is a state per variable. If it's a symbolic variable, when you do a copy operation on a symbolic variable, you copy the state. And the variable that where you're copying to becomes symbolic as well. It's just a simple propagation.
Okay, thank you.
Hey, thanks for the good talk. This is kind of like a two-part question here. So I guess the first question is, have you looked at other binary analysis frameworks like Anger, for instance?
We don't need to do binary analysis in this case because we have the source code.
Right.
So it makes it a lot easier. But yeah, I've compared other, like S2E is a great project.
Right.
And the only downside is the performance. If not the performance, then that's exactly what we're looking for.
Right. So the second part to my question is more about sort of like methods and approaches, right? So with Anger and some of these other program analysis frameworks, they've kind of solved a lot of these, I don't want to say solved these problems, but they've handled or dealt with a lot of these problems that you've kind of described, right? So from the standpoint of symbolic execution, you have your dynamic symbolic execution, your static symbolic execution, you do like state merging to kind of deal with namespace problem or like state explosion problems. So are you going to look at implementing some of these approaches?
Definitely. So that was the next, I guess, constraint optimization. So take all those optimizations from frameworks like Anger, from S2E, all the other projects, and try to implement them. But for now, this was just, again, just a proof of concept to see if it works. And if the idea is working, then you can start adding features.
Okay, great. All right, thanks.
No more questions? Well, thank you.